Welcome back, everybody. And in this unit, we're going to be talking about wildfire. And this is actually one of my areas of expertise, so I'm particularly excited to talk about this topic. I think wildfire illustrates a lot of really interesting things about how the Earth system works and how it interacts with us, people living on the Earth. So, our goals for this lesson are first for you to understand wildfire's role in the Earth's systems, and then to be able to evaluate proposed approaches to reducing wildfire disasters. So, starting by looking at fire's role in the Earth's system, we can think of Earth as really being the fire planet. Right? So, our name is Earth, but in a sense, a fire is one of the most unique things about the Earth. Because fire is made possible by our high amount of oxygen in the atmosphere and the availability of plants for fuel. And no other planet or moon or star or anything else that we know anything about has those conditions. So we do not see fire happening on other worlds the way that it happens here on Earth. Now, maybe in the future, we'll discover something about some of the planets we found around other stars, and we'll find ones that have as much fire as the Earth does. But for now, fire is one of the things that really makes our planet unique. So not only can we have fire on the Earth, but we have a lot of it. Nearly every terrestrial ecosystem can burn, and many of them depend on fire. Fire is actually a necessary part of many of our ecosystems on the Earth, outside of a very few like Arctic tundra and some of the equatorial rainforest areas. Just about everything else, fire is part of how that ecosystem operates. It's a necessary element of the ecological cycle. And fire plays a key role in many of our biogeochemical cycles. So in this lesson, we're going to be talking in particular about fire's role in the carbon cycle, because we're going to be connecting it up with the things that we've learned about climate change. But fire also plays important roles in the water cycle, in the phosphorus cycle, in the nitrogen cycle. So many of these important cycles that link together all of the different aspects of our Earth are heavily affected and shaped by fire. So let's first try to figure out, well, what is fire? We can define fire as a rapid exothermic oxidizing reaction. So fire is a chemical reaction. It's not a substance. So you may have heard of like the ancient Greek idea of the four elements, where you had earth, water, air, and fire. And so they thought of fire as like stuff, as a substance. But we now understand that fire is a process. It's a chemical reaction. It's a thing that happens. And it's a rapid exothermic oxidizing reaction. So what that means, first, rapid, it happens quickly. It happens a lot more quickly than comparable reactions that might produce similar end products, but that happen on a slower scale. So for example, digestion, if you eat something and digest it, that chemical reaction is actually very similar to what would happen if you burned that thing. But digestion takes a lot longer, whereas fire happens quite quickly. It's exothermic, which means it releases energy. It produces more energy than it takes to get it going. So when you have a fire, energy is coming off of it. And that should be pretty obvious. If you've encountered fire, it's producing a whole bunch of energy. And it's an oxidizing reaction, which means it's taking oxygen from the atmosphere and combining it with stuff to make new compounds. So it's making stuff out of oxygen from the atmosphere. And I've written out a simplified version of the chemical reaction formula for fire and for photosynthesis, because fire we can think of as being inverse photosynthesis. So when photosynthesis occurs, you've got a plant and it's taking in H2O, water, through its roots. It's taking in CO2, carbon dioxide, from the air, and it's taking in energy from the sun. And it combines those things and it produces oxygen, and then it produces the various hydrocarbons that are the building blocks of the plant. So when the plant is growing, it's growing out of these various sorts of molecules that are made out of combinations of carbon, hydrogen, and oxygen that are produced in the process of photosynthesis. So it's taking in energy, water, carbon dioxide, producing oxygen that goes back into the atmosphere, and then all of the molecules that the plant itself is made up of as it grows. Then if an animal eats that plant and digests it, the animal also needs to breathe in some of that oxygen, pull the oxygen back out of the atmosphere, combine it with those molecules from the plant, and that will produce water, carbon dioxide that's breathed out by us animals, and it'll produce energy. That's why we eat plants. We can get the energy back out of them by digesting them. Fire does the same thing. It just does it much more quickly. So fire will also take all of those molecules that our plants are made out of. It will take oxygen from the atmosphere, it will combine them, and it will produce H2O. So there's water in the form of water vapor that comes out when we have a fire. It produces CO2, carbon dioxide, and it produces a whole bunch of energy. So fire is really just photosynthesis in reverse. So the characteristic thing that we think of if we're imagining a fire is specifically the flame. So the flame is a product of the combustion reaction that is happening, right? So we've got that chemical reaction that I described on the previous slide, and one of the things that will result from that is usually a flame. Because a flame is glowing hot gases that are being released because the fire is vaporizing elements from the fuel. So as bits of the fuel that are being consumed are being turned into gases that are then coming off of the fire, and they are so hot that they are glowing. Right? They are giving off electromagnetic radiation in the visible light portion of the spectrum so we can see them. And so that is what the flames that come up off of a fire really are. They're those glowing hot gases. That's why they flicker and move. They're being blown around by currents in the air. And so this is, as I said, releasing this electromagnetic radiation. So we're essentially seeing, if we think all the way back to our discussion of energy, is that the chemical potential energy in the fuel, so the chemical potential energy that's in the wood that's burning or the wax that's burning in the candle that you see in the picture there, that chemical potential energy is being converted into electromagnetic radiation energy that is then coming off of that fire and that we are feeling as heat and seeing as light. So each reaction, so each time we stick a oxygen molecule together with a fuel molecule and produce those byproducts, needs to produce at least enough energy to trigger the next reaction. So each of those reactions requires a little bit of energy to get it going, to trigger it. Right? Things don't just spontaneously burst into flame. They need a little bit of energy to prime the pump and get them rolling. And then they will continue to go as long as they're producing enough energy in the process to trigger the next bit of fuel to burn. So fires become self-sustaining if they're producing enough energy to keep triggering the next bit of burning to happen. And so in describing that, I'm starting to get into describing the fire triangle. Now, there are actually 3 different fire triangles. So I'm going to go through these one by one, starting with the finest scale in both time and space, and then working out to the larger scale fire triangles. So if we start with what's shown in red there in the lower left corner, this is the classic fire triangle that describes what's necessary for combustion to occur, for us to have a fire burning at all. We need 3 key elements that are the 3 legs of that triangle. We need fuel, so we need something to burn. And that's usually some sort of plant material, but other things can burn as well. Then we need oxygen that is typically coming from the air. In certain other applications, like in a rocket engine or something, you might be supplying oxygen directly from its own supply or something. But most of the time when we're talking about fire, we're talking about oxygen that's coming from just the general atmosphere. Uh, and then we need heat. So we need that little bit of heat to kick off the process, and then we'll release more heat as things burn, and at least some of that then will be the heat that kicks off the next bit of the process. So we need those three things for fire to be able to happen, which means we can put out a fire by removing any one of those three legs. So if you were to just let your fire burn out, not add any more fuel to it, you're not stick any more logs on the fire, eventually that fire would run out of fuel and it would go out. So you can deprive it of fuel. That's often how we control the spread of a fire. So if you're making a campfire, that you clear the area around the campfire, remove all the fuel so that it doesn't spread into anything else. You can remove the oxygen, and that's what those little bell-shaped candle snuffer things do. Right, that's the principle behind one of those is you put that over the top of your candle, and that restricts new oxygen from getting into the flame. And so the little pocket of air that you've got there around the top of the candle runs out of oxygen. It can't get any more, and so the fire goes out. So you can deprive it of oxygen, and then you could deprive it of heat. And that's basically what you're doing if you throw water on a fire. So if you throw a bunch of water on a fire, then that water is going to consume a lot of the fire's energy as it gets evaporated. So in order to keep the fire going, you got to get rid of that water. You got to get the water out of the way by evaporating it. And so we talked about evaporation pulls in energy. So all of that water evaporating off of your fire sucks up a lot of that energy. And if you put enough water on the fire, then that sucks up enough energy that there's not sufficient heat to trigger continued combustion. Right? We don't have that little bit of extra energy that makes the next round of burning happen. So you can take away any one of those three legs of the fire triangle and you'd put out the fire. You need all three of those in place for burning to occur. So that's on the scale of a burning object. We can see the operation of that basic fire triangle when we're looking at just like a candle or a campfire. When we zoom out to the landscape scale, we get the wildfire fire triangle. So that's the one in the middle of this diagram in orange. So here we're looking at the key elements that shape how fires burn across a landscape. So a large area having a fire moving across it. So in this case, fuel is still an important part. What kind of fuels are on your landscape will shape how your fire burns. So here we're looking not so much at, do we have like another log in the fire? We're looking at the overall characteristics of the ecosystems that this fire is moving through. We're looking at things like what species of plants are growing here, because some species burn more easily than others. We're looking at how well those fuels are connected to each other. So the fire is burning in one tree, can it make it to the next tree and catch that one on fire? We're looking at the characteristics of that fuel in terms of things like, is it wet, is it dry? So fuel becomes one of our legs of the wildfire fire triangle. Then we have weather. So the atmospheric conditions play a big role in shaping how fires burn. So obviously, if it's warmer out, that encourages fires to burn more readily, burn more intensely, more hot. Having moisture in the air, on the other hand, will tend to decrease your fire. And especially if you've got precipitation falling, that's not good for the continued burning of your fire. Wind plays a big role as well. Wind can drive fires in certain directions, so they'll burn towards one direction and not in another. They can push fires to jump over barriers. So if you have a stream or a road or something where there's a gap in the fuel, if you've got good wind, that can pick up burning embers and toss them across that barrier so that the fire can move into new areas. So weather plays a big role, and then topography. So fires burn best going uphill. So that's because we've got those flames, right? That hot gas coming up off the fire. Fire is blasting all this heat upward. And so if you've got things that are uphill, the fire will heat those things up and get them to burn more easily than if it's trying to burn things downhill of it. So fires move very quickly up hills. And so if you are watching how a fire is moving through the landscape, you can expect the topography to really shape what areas burn quickest and what areas the fire moves into more slowly or doesn't move into at all. So our wildfire fire triangle is composed of fuel, weather, and topography. Then at the broadest scale, we can define a fire triangle for a fire regime. And so in order to understand this, first we have to figure out, well, what is a fire regime? So a fire regime is the type of fire typically experienced in a place. So now we've moved from an individual fire event into talking about the types of fires that occur looking over a long period of time where there might be multiple fires within that stretch of time. So another way to think of it is you can think of the fire regime as being comparable to an individual fire in the same way that climate is comparable to weather, right? So we talked about weather is the current whatever's happening in the atmosphere, and climate is long-term average conditions. So you have the same kind of relationship between an individual fire that might be burning and the long-term average types of fire that that place would expect to get. And when we're describing a fire regime, there are three major things that we use to define a fire regime and use to compare different fire regimes to each other. So these are frequency, intensity, and seasonality. So frequency tells us how often does this place typically get a fire. So some places will burn every year. Right? There are some ecosystems that can catch on fire and have a fire in the same place every single year. There are other ecosystems where fire is part of that ecosystem, but only happens once every, say, 500 years. So, you may have a very long distance in between fires in an ecosystem like that. So you're getting very frequent fires, or you're getting fires spaced out by a lot of time. That's your frequency dimension. Intensity is how hot the fire burns and how much of the vegetation is consumed. So some fires are very cool. They're not, obviously they're hot. You don't want to stick your hand in it, but they're comparatively cool. They're not burning very intensely. They're not consuming lots and lots of fuel. And those kind of fires we often find running along the surface of the ground. So we call those surface fires. They're mostly consuming things like grass, fallen leaves, and branches that are laying on the ground. But a really intense fire, one that's going to burn a lot hotter and is going to consume more of the fuel. It's going to be burning up everything in its path. And those more intense fires often become what we call crown fires. So they move up into the upper story of trees and bushes and things that are in that location. So we're consuming the entirety of those fuels, getting a much hotter, more intense fire in that case. We also have seasonality. So seasonality is when during the year do fires usually happen. So some places have their fires usually in the winter, some usually in the summer. Here in Pennsylvania, our fire seasons are actually two different slots during the year. We tend to get fires in early spring and late fall. And that's because here, what you need is the intersection of it being warm enough for the fire to keep burning, because if it's too cold, like it is in the winter, a fire is not going to be able to continue burning very easily. But you also need to not have leaves on the trees, because the leaves on the trees create a lot of shade. They keep a lot of moisture in that environment, and that also inhibits fires. So we tend to get our fires here in Pennsylvania either very early in the spring when it starts to get warm but the leaves aren't out yet, or late in the fall when it's still, it hasn't gotten totally cold yet and all the leaves have fallen off of the trees. So different places will have fires typically occurring at different points during the year, and therefore at different points during the life cycles of the plants and animals that live there. It makes a big difference if fire is burning, say, when all of the baby animals are still in their eggs versus when they have hatched and grown up enough to be running around, for example. So frequency, intensity, and seasonality describe the types of fires that you might have in a particular location. And this is important because species and ecosystems depend on regular disturbances, such as fire, to maintain themselves. So this fire regime becomes an important part of the ecology of that area. So some of the key things that a disturbance like fire can do for an ecosystem are that they can open up space. So if you have a forest that's been growing for a long time, it's full of trees and full of fallen branches and lots of other stuff that has grown up there. And so that doesn't leave a lot of space for new things to grow. It's kind of all occupied. So a fire, by clearing some of that out, will create space for new things to grow, and in particular create space for species that might need more space, that might need more sunlight getting in. And so then that ecosystem can maintain different kinds of species that require different kinds of conditions if fires occasionally alter those conditions and burn away some of the accumulated older material. Fires also release nutrients into the ecosystem. So those old growth has a lot of nutrients locked up in it. If you have the trunk of a gigantic old tree, there's all kinds of important nutrients that make up part of the wood of that tree that are just sitting there. They're not cycling in the ecosystem. So by burning that, you release all those nutrients. And so other new growing individuals can pull on those nutrients and use them for growth. And so fires then help to enable new growth to be happening. So you got a lot of vigorous new growth happening in ecosystems after they've experienced a fire. And there are many species that depend on having these fires in order to enable them to grow their best. So the photo that I've got there is of a blueberry farmer looking over his harvest. And so blueberries are a fire-dependent species. For blueberries to grow their best, the bushes actually need to burn. They need to experience a fairly cool fire, not a very intense fire, but they need some fire to prune back old branches and stimulate further growth. So after a wildfire, you can get a bumper harvest of blueberries, and many blueberry farms will actually deliberately light fires on the farm in order to stimulate those plants to grow. So any ecosystem and species within that ecosystem are going to be adapted to a specific fire regime. So it's not that they're adapted to fire or not adapted to fire just sort of in general, they're adapted to a particular fire regime. So some species are adapted to a high frequency fire regime. They need fire to happen very, very often, every few years. Other species may be adapted to a low frequency regime. That they need fire to happen, but they need a lot of space in between the fires to grow and put out seeds and get ready for the next fire. Some species depend on a very low intensity fire regime. They need fire, and they need that fire to be cool and kind of consume some of the litter on the ground and prune back some branches, but not kill off entire plants. Other species might be adapted to a high intensity fire regime. They need a fire to kill everything and just sort of wipe the slate clean so that things can grow back after that. So species are adapted to particular fire regimes, not just to fire in general. So here's what those fire regimes look like in the United States. So what they've got here is they've classified fire regimes according to their frequency and their intensity, which is also sometimes referred to as severity. This is another one of these things where we have sometimes different terminology here. So they're kind of leaving the seasonality part off of it for the sake of simplicity. And so what you're seeing here is some parts of the country have a typically low frequency fires, where sometimes as much as 200 years between fires in places you can see like New York, New England, some parts of the Southwest. Other areas have much more frequent fires. So less than 35 years between fires. And if we broke it down more, we could see some of these fire regimes are even more frequent than 35 years. They just kind of grouped it that way for simplicity on the map. And then we have different levels of severity. So some have low severity, so the fire burns relatively cool, consumes only some of the fuel. Others have high severity, or they're describing it here as replacement severity, where they replace the entire vegetation in that area by burning down everything that was there before. So again, you see that range of different fire regimes. If we zoom in on Pennsylvania on this map, you'll see that most of the state is in the sort of pinkish color there that represents a less than 35-year frequency, so very frequent fires, and low to mixed severity. So most of Pennsylvania historically experienced very cool fires kind of moving through the understory of the forest, burning dead leaves and branches and stuff that have fallen down, some of the small plants, dead grass and stuff, but usually not harming the adult trees that were growing there. So that was sort of the typical fire regime for most of Pennsylvania. But then you can see kind of the northern tier of the state is in some of that darker green that has a much longer periods between fires, so a much lower frequency fire regime in the northern bit of Pennsylvania, more similar to what we see in New York and New England there. So now we can back up to the fire triangle slide and look at some of the factors that are shaping these fire regimes. Why would we have different fire regimes in different places? So here, the first factor is vegetation. So what kinds of ecosystems are growing in that place? Because different sorts of species will be suited to different types of fire. They provide better fuel or take longer to provide fuel. They hold moisture in or become very dry. Some species have a lot of oils in them that are very flammable. So just the characteristics of the species of plants that are growing there, and then also the arrangement of those plants. Are those plants that tend to grow very close together, so fires can easily spread from one to the next. They tend to grow far apart, etc. Then we've got the climate. So just like weather affects individual fire events, the climate affects the fire regime. So things like how hot is it? How much moisture do you tend to get? How much variability is there in those factors? Right? So climate affects your overall fire regime. And then your sources of ignition play a big role as well. So what are the things that actually tend to start specific fire events? And so there's two main categories of ignitions that we would want to pay attention to, which are lightning and people. So a lot of fires can get started by lightning. So if you've got a lot of lightning storms, and especially if they tend not to be accompanied by really heavy rain that would put out any fires that the lightning started, that's a source of ignition, and it'll follow certain patterns, right? You get those lightning storms at certain times of the year, for example, so that will affect the seasonality of the fires that get started by that lightning. Then people start a lot of fires. So sometimes we start fires deliberately. We start them as a land management strategy. We start them to commit arson, to like get insurance money or something. Or we start them accidentally. We don't put out our campfire well enough. We have power lines that fall over into branches and get sparks going. We have cars that get really hot when we've been running them too long, and you park over some dead grass, and it creates enough heat to light that grass on fire. So there's a whole bunch of things that people might do that might ignite fires. And so human activity plays a big role in shaping fire regimes. Are people causing a lot of fires at certain places in certain times of the year, etc.? And are people putting out those fires? Because people can be kind of an anti-ignition if we put a fire out. Even if it's a fire that started, say, from lightning, if people put it out right away, that's another human influence on the ignitions that will then go on to shape that fire regime. So the kind of vegetation you have, the kind of climate you have, And the sources of ignitions, whether it be natural causes like lightning or human causes like people starting and putting out fires, those things will shape what kind of fire regime that you have in a place, and will also cause changes in that fire regime. So fire regimes can be altered by altering any of those three elements of the fire regime fire triangle. So if we alter the climate, we can change the fire regime. If we alter what we're doing about ignitions, we alter the fire regime. If we alter the kind of vegetation that's present in a place, we can alter the fire regime. So to dig a little more into the human role in fire, fire is one of humanity's oldest tools for large-scale alteration of the environment. So some of the earliest evidence that we have of human activity having an impact on the larger environment comes from evidence of people lighting fires in the past. So we can go back tens of thousands of years and we can see evidence that human activity was causing changes in the amount of fire that was happening in certain parts of the world. We often see as a significant change in fire regimes in places at the time that humans first arrive there, because now people are deliberately either lighting or putting out fires, and that affects that fire regime, and we can see evidence of that in the archaeological record when we look at charcoal that's been preserved in sediments and so forth. So fire goes way back. Humans have a very close relationship with fire. And if we look at the use of fire by traditional and indigenous communities, we see a wide variety of things that people might use fire for, a wide variety of reasons that people might deliberately light fires. So we might light fires to clear land. So fire, especially in the absence of power tools, is a pretty efficient way of clearing out the vegetation from some area that we want to use for something else, that we want to turn into a pasture or a farm or build stuff there. Burning off what's there is an efficient way to clear that land. People use fire for hunting. So you might light fires in order to chase your game in a certain direction. So, because your deer or whatever might not want to cross through where the fire is, so they're going to run the other direction, and then hunters are waiting there to kill them. Right? You can make the whole process easier by using fire to chase your prey, or just to flush it out of places that it might be hiding. So if you clear out some of that vegetation, then you can see the things that you're trying to hunt more easily. People use fire to encourage new growth. So we saw the blueberry farmer in the earlier slide, and that's just one example of many kinds of plants that will have vigorous new growth after they've been burned. And that new growth may either be something that people want to use directly. So we may find that new growth is, maybe that's something that we're going to eat, like with the blueberries. Maybe it's a plant that we're going to use for something else. So like the new shoots that grow up might be nice and straight, so we can use them for basket weaving or something. And then also that new growth might attract animals to come in to eat it that we could then hunt. So it was pretty common for hunters to lie in wait in areas that had recently been burned. As that new growth was coming up, that would attract in animals like deer or kangaroos in Australia that you could then hunt. People also did that to improve pasture for cattle and sheep, because cattle and sheep like to graze on the new growth that comes up after a fire. You can burn stuff for pest control. So if you burn off an area, that's going to set back the tick population, for example. And so that can help control unwanted organisms in that way. You can burn for hazard reduction. So if you have burned off an area, then if you chose when to burn it under circumstances when you knew what was going to happen, that it wasn't going to get out of control. Now you've reduced the amount of fuel that you have in that area, and so you're less likely to get a big, really dangerous wildfire burning there. People light fires for warfare purposes. So if you've got the enemies coming towards you, you might light a fire that's going to blow towards them in order to attack them using fire, or you might light the fire to try to burn down their supply depots and stuff like that. So there's a lot of use of fire in warfare. And then there are ceremonial uses of fire. Lighting fires as a way of enacting the human connection to the land. And so I've got the expression there on the slide, cleaning up country. And this comes from indigenous people in Australia. This is a way that they often describe the importance of using fire. So in indigenous Australian culture, it's not just that fire is a useful tool for producing various sorts of effects, but it's actually one of the responsibilities that they feel that they have as people towards the ecosystems that they live in. That's the role of people, the contribution of people to the larger ecosystem is that people are the managers of fire, and that people have a responsibility to burn in certain places at certain times of the year. And so if an indigenous community has been forced off of their land for a while, then they come back to see that land and they see the effects of not having been burned as often. So there's overgrowth of plants and stuff. They may describe that as that country needs to be cleaned up, that people are failing at their responsibility for not playing their part in how those ecosystems are supposed to work by applying fire to the landscape. Okay, so now we want to connect fire into our discussions of natural hazards. So that's been our through line in this course. So fire as a hazard. And so in some senses, this should be pretty obvious, right? Of course, fire is hazardous to people, but it's useful to break down exactly why. So what kind of threats can fire pose to us? Well, the most obvious one is the loss of life and property from getting caught in a fire, right? It's obviously bad for you if your house burns down in a fire, or your business burns down, or if you or someone that you care about gets caught in that fire and burns to death. That is clearly not good. So there's that very direct threat of being caught in the fire itself. Then we also have the risk from smoke inhalation. And so this is actually a even bigger threat to health than the flames themselves. So most people that die in a fire, whether we're talking about a house fire or a wildfire, most people who die in a fire die from smoke inhalation, not from being burned by the flames. You might die of smoke inhalation and then your body gets burned afterwards, but it's the smoke is usually the direct hazard. So it can become incredibly difficult to breathe if you are close to a fire. And so people can lose their lives from smoke inhalation. And then that smoke can spread much farther than the fire itself spreads. So the picture you have here is the air quality map from, I believe it is this past summer. We had these big fires up in Canada. And this has been happening, many years recently. You have these big fires, and the smoke plume spreads out across practically the whole continent. So all of the gray areas there are the plumes of smoke from the various fires that were burning at this time. And you can see how most of both Canada and the United States, and even down into Mexico, are experiencing the smoke from this fire. You may have noticed that this past summer, that there were some days when you could sort of smell the smoke in the air. It might have been a little harder to breathe, especially if you have asthma or some other breathing condition. You could even sometimes see it in the sky, and we've got some really brilliant sunsets out of it, because as the sun's light's coming through all of the particles in the atmosphere from the smoke, it makes a really pretty sunset, but it's also an indication that the air is not particularly clean. You can actually then see that on all of the air quality monitoring stations that are all the little dots there. You can see large portions of the eastern United States are yellow, orange, red, and even purple, the highest level of danger from this wildfire smoke. So smoke can then have really broad-reaching consequences, and there have been various attempts to calculate the number of people that suffer from health complications from wildfire smoke across the whole country or continent as a result of these fires. So smoke inhalation can be a big health problem. We can also get water pollution. So the ash from fires washes into our rivers and lakes and so forth, and can pollute those water sources. And it's especially risky if what has burned has not just been trees and grass, but has been various human-made materials that we really don't want in our water. So we get a lot of problems with plastics, for example. If houses and cars and stuff have burned in the course of a wildfire, and those plastics have given off a lot of different sorts of chemicals that then both get into the air in the smoke or get washed into waterways, those can be serious pollutants, alongside just having lots of ash and charcoal in your water supply. That's not great either. You can get erosion and landslides following a wildfire, because if a wildfire is consuming all the vegetation, then that is exposing that area to greater erosion, because those plants are not protecting the soil anymore from precipitation, and so you can get accelerated erosion. You can get big landslides happening after a fire. If you get like a fire that burns off all the vegetation, and then you get a big rainstorm afterwards that saturates the soil, and sometimes those post-fire landslides are more deadly than the fire itself, because they can come on a lot quicker, and people are already, stressed and distracted dealing with the aftermath of the fire. You get ecological damage from alteration of fire regimes. So when you have species that are adapted to our particular fire regime, if you change that fire regime, then that could cause serious problems for them. And in this case, this can be a risk of both too little and too much fire. So if you have plants that are adapted to low severity fire regime, and then you hit them with high severity fire, they may not be able to recover from that. They may have destroyed more of the plant than they were adapted to deal with losing. On the other hand, if you have an area that is adapted to a high frequency fire, and then you increase the frequency, so you add more time between fire events, that may impair the reproduction of certain plants that need that fire to stimulate the growth of the next generation. So both too little and too much fire can present a hazard. So let's look at the fire that we're getting in the United States. So this is a graph of acres burned in the United States from 1983 up through 2020. And looking at this graph, there's a pretty clear upward trajectory. So we've got lots of year-to-year variation, right? You might have a really big fire year with lots of area burned, followed by a very quiet year with little burning, but overall the trend is upwards. And in this case, I'm looking at acres burned because I think that's a better variable to look at than number of fires, because number of fires, you might have two fires and then they combine into one. That doesn't mean there's less fire happening just because you now have one fire instead of two. It's just those two fires have merged into one big one. So looking at acres burned, I think, is a better variable here. And we can see there's clearly an upward trend since the 80s. So the risks posed by fire in the United States definitely seem to be increasing over the last 4 or so decades. However, something interesting happens if we zoom out time-wise. So here is a similar graph that goes all the way back to the 1920s. And so what you can see, if you look at just the portion from 1983 to present on the graph, this graph looks the same as the previous one, right? They're both drawing on the same data set from the US government. So you're seeing that upward trend over those decades. But compared to that, that's seems like nothing compared to what we were having burn in the 20s, 30s, 40s. So there's clearly something going on here, right? And there's actually two things going on here. There are differences in the data that we have and differences in the actual behavior of fires. So part of what we're seeing here is a difference in the data that we're collecting. So from the 80s onward, we've got satellite data. This has been kind of a theme in this class, right? The satellite data changed a lot of things. And so satellite data allows us to get some very exact measurements of the amount of area that burns in a fire, right? Because we've got satellites going over, taking those photos of the Earth constantly. And so we can get a very clear and accurate and detailed idea of exactly what area burned in a fire. In the past, we didn't have quite such exact data. We had to send field teams out to walk around the fire and map it out and measure it. And that process can end up uh, giving higher numbers than the satellite data would, because a lot of fires are patchy. So they burn some stuff and they leave some bits unburned. And with satellite data, it's very easy to count only the areas that were actually burned and leave out all of the little patches. If you are out there in the field kind of trying to measure the border of the fire on a map yourself as you're hiking through it, it's more difficult to account for that patchiness. So a difference in the data collection strategy, the source of the data is one thing that's going on here, but it's not the only thing, right? And we can certainly see big changes in the area burned even before satellites came on the scene. So another important thing that's happening here is the rise of fire suppression. So back in the 20s, we had very little ability to put out fires that were burning, especially in places like out west, where you have large tracts of land with very few people living on them, lots of flammable vegetation. If a fire gets going out there, in the 20s, it was very difficult to do anything about it. It would just end up burning, and lots of areas would get burned. But as we move into the 30s, we have the Great Depression. And one of the things the US government did in response to the Great Depression was to create the Civilian Conservation Corps. So this is a national jobs program that was meant to put unemployed men to work, excuse me, doing useful things for the country when they couldn't get jobs in the regular economy because we were in the Great Depression. And so one of the things that the CCC did was to improve our firefighting infrastructure. So we had some crews that became firefighters. So we increased the number of people working as firefighters on public lands. And then we also improved the infrastructure that we had for firefighting. So we built new roads, for example, that could be used to easily get people into an area to be able to put out fires. Then we move into the 1940s. In the 40s, we have World War II. And at the end of World War II, we have a huge surplus of military equipment, a whole bunch of stuff that was made for the war effort, and now the war is finally over. What do we do with all these planes and helicopters and things that we built? Well, one thing they did was sell them off cheap to the Forest Service to use for aerial firefighting. So that includes aerial surveillance, so you could fly a plane over and you could spot ignition. So if lightning struck deep in the wilderness, it would get noticed more quickly and you could send people out to do something about it more quickly. And for dropping water and fire retardant on fires, especially in remote areas that otherwise people couldn't get to, and also for bringing personnel in. So if you need to get a wildfire crew out to the fire quickly, if you had aircraft and other military surplus equipment, you could do that much more quickly. So this enabled the Forest Service and other US government agencies to really emphasize fire suppression. So we started trying to put out every fire. They adopted a policy that was called the 10 a.m. policy, where basically if a fire started somewhere, the goal was for it to be totally out by 10 a.m. the next day. So of course they didn't always manage this, but that was their stated goal. So there was a big effort put into fire suppression. And so that brought down the amount of fires happening by a pretty dramatic amount. So we're seeing much less burning. And so we hit this kind of low point in the middle of the 20th century. Right? We're looking at the 60s, 70s to the beginning of the 80s is this kind of low period where the country was very successful at suppressing most of the fires that were happening. But then since the 80s, we've seen that upward trend. So despite the fact that we have increasing technology for dealing with fires, we have much better surveillance to catch things as they start, much better technology for trying to put fires out, we're still seeing more area being burned. We are losing ground in this effort to put out all of the fires. So what's going on here? What explains changes in the risk posed by fires in this country and other places? Well, there's basically three things that make contributions to changes in fire risk. And a lot of the debate about wildfire is really a debate about how to prioritize these three different factors. Which one do we think is the most important? Which one should we be putting our efforts and resources into addressing in order to reduce fire risks? So these three factors that are all in play, but lots of debate about the relative contributions, are housing development, land management, and climate change. So let's look first at housing development. So if you remember our discussion from an earlier lesson, we talked about the fact that disasters are the result of a combination of a hazard event occurring and people being vulnerable to that hazard event. So if our hazard event is a wildfire, one of the things that could make people more vulnerable to that fire is just living close to it. Right? If we have more people living in fire-prone areas, then more people are going to be harmed by wildfires. And we are seeing a trend towards more people living in fire-prone environments. So this is described as the growth of the wildland-urban interface, or WUI. So if you go to talk to fire personnel, you'll hear them talk about the WUI a lot. So the wildland-urban interface is the zone where settlement, so places people are living, abuts flammable landscapes. So where you have a landscape that is able to burn and you get people living right next to it or scattered within it. So what you're seeing on this map here for the lower 48 states, and the yellow and orange are different types of WUI. So there's specific definitions of those that I won't get into here. The green are vegetated areas that are non-WUI. So they're areas that have low or no housing. Right? So nobody's living there. It's just the wildland part of it. And then you see other areas that are either urbanized areas, so no wildlands because it's built up as like cities and suburbs, or that are things like agricultural lands. That's the lightest kind of tan color there, that aren't going to catch on fire. A cornfield's not going to burn the way that a forest would burn. So you can see lots of WUI areas all around the country. If you focus in again on Pennsylvania, you'll see the red spot that represents Pittsburgh and its immediate suburbs. It's the urbanized area. I don't have to worry about a forest fire at my house because I'm just surrounded by other houses. There's no forest here. But then as you get out into the areas around Pittsburgh, so the outer suburbs, the various townships in other parts of Allegheny County and Butler County and stuff, you see a lot of the yellow and orange there. So we've got a lot of wildland urban interface in these areas. We've got forests and people living right there beside or in those forests. So we're seeing a growth of WUI landscapes all around the country. And this is due to a combination of, on the one hand, sprawling housing patterns. So we are building our new houses farther and farther out from the centers of our cities. If you look, for example, at Pittsburgh, you'll find that the city of Pittsburgh has been losing population every decade since, I believe it was the 60s was the peak population for the city of Pittsburgh, like the actual city boundaries that are governed by the mayor and council of Pittsburgh. But if we look at some of the more outer suburban areas around Pittsburgh, including places in Butler County like Cranberry or the city of Butler, right, these outer areas that are out closer to the wildlands have been growing. And that's a pattern that we see in lots of our cities, that even if the central part of the city is declining in population, the areas around it out into the suburban and rural areas are growing in population. And so we're building new houses and creating new WUI areas. The other factor is a loss of agricultural buffer zones. So classically, you'd have your city or your town, then you'd have agricultural fields surrounding it, and then the forests and other wildlands out beyond that. You had this kind of buffer zone of farmland in between where people were living and where the flammable forests were. But in lots of areas, we've been losing that. So here in Pennsylvania, a lot of our farms have been going out of business and then regrowing into forests. So what used to be a field that would buffer you from the nearby forest is now the forest is encroaching and coming close to you. So these different processes are leading to increased WUI landscapes and therefore increased risk to people from wildfires. Having people live in the WUI also can cause more fires to happen because human activity is a major source of ignition. So if you have more people in the woods, more chances for somebody to throw a cigarette butt out the car window and have it start a fire, or start a campfire and not put it out adequately, or have power lines that are going to more people's houses and that can spark a fire if branches fall on them. So if housing patterns are the key to our increased risk, then that would suggest that dealing with those housing problems, housing patterns, is our solution. So one thing you might think about doing is restricting development in the WUI. Basically saying certain areas are too high fire risk and we can't build more houses there. That kind of policy has been tried in some places, and it's usually incredibly unpopular. People that want to live in pretty areas don't want to be told that you can't do that because the fire risk is too high. Developers that are going to make a profit off of building there don't want to be told not to build there. Communities that were hoping for tax revenue from having people move into new developments don't want to be told that they can't do that. So that is a theoretical possibility. It's not one that's been super popular or successful thus far. But when we do build houses, there are various things you can do to make those houses safer. So even if a fire does burn through that area, the house will not be as likely to be damaged, and people in that house might be protected. So the fire won't be doing as much damage, right? That hazard won't become as much of a disaster. So there are a whole bunch of things that can be done. This diagram summarizes some of them. They include things like clearing vegetation from immediately around the house, removing leaves and other debris from gutters and so forth, having a hose available to put out embers that might fall there, etc. Building your roof out of non-flammable materials, so using like tile or metal roof rather than wooden shingles that could catch on fire. So there's a whole list of recommendations. I'm not going to go through all of them in this presentation here, but there's a whole bunch of things that you can do to make your specific house that you've built more fire safe. And so those are things that some people can do just by their choice. They can decide, I don't want my house to burn down. I'm going to invest in getting these things done. There may be incentives from insurance companies. So insurance companies may give people a break on their insurance if they have adopted fire safe practices, because that means you're less likely to need to get a payout from the insurance company. So it's good for their bottom line, and then that gives you an incentive to do it because you're going to save some money. And you might also have regulations forcing people to do that. So some communities in fire-prone areas have created laws that all new housing has to meet certain standards in order to be more safe from fire. So that's how you might address the component of fire risk that comes from housing development in fire-prone areas. So then a second component is land management, how we deal with the land that then ends up burning. And so we've touched on one element of this already, which is the issue of fire suppression. So suppression, on the one hand, can be a way to reduce that risk. If a fire starts, we can go put it out, and then it won't harm the people that might have otherwise been in its way. So we apply our various resources, personnel, technology, etc., to put out those fires. And the most common way that we do that is by removing fuel using either hand tools. So you see the fire crew here in the picture. They've got various hand tools like hose and chainsaws that they're using to strip the fuel out of a barrier, basically, to the spread of a fire. So a fire will hit that spot, there will be no fuel to consume, and so it won't progress any further. You can also use mechanical means to do that. You might send a bulldozer through to push all the fuel out of the way. You can also use back burning. So you might deliberately light some of that potential fuel on fire to try to get rid of it before the main fire comes through. So removing fuel is usually our method for suppressing a fire that once it's gotten going. You will see on the news these really spectacular aerial drops of water or fire retardant. And the fire retardant, they often put a chemical in it that turns it pink so they can easily see where it's going. And so you see this plane go over and this big, wave of pink stuff drops out of the plane. That looks really cool on the news. that tends to be ineffective for fighting large fires. So that can be used to protect certain specific targets. So if you have a house that's in the path of the fire, you might drop fire retardant right on that house to help protect it. But you're not going to put out the entire fire by doing that. You're just not going to be able to get enough water and fire retardant up into the air and onto the fire in time to do it. So suppression can be a way to protect people from fires. The catch with suppression is that the longer you do it, the harder it gets. So here's a comparison of a landscape. You can see from the shapes of the mountains that this photo is taken from the same vantage point in these two different years. You've got one from 1936 and one from 2012. And this is an area in the Pacific Northwest that was subjected to some pretty good fire suppression. They put out all the fires that would have started in this area. And what you can see is that in 1936, you had this mixture of forested areas and open grassy areas. So you had, a lot of more spotty trees in the landscape, lots of other stuff growing in between the trees. You look at 2012, and you've got this blanket of trees covering the entire landscape, very dense forest. And that's because we had fire suppression in this area, and so fires were not consuming any of that fuel. It allowed these trees to just grow and grow. And if you go into the understory of this forest, you would find that is just chock full of stuff. There are other plants growing in there. There is dead branches and things just filling up the understory of that forest. So the 2012 picture there is showing you a landscape with a lot more fuel on it. So if that fire suppression were to slip, if a fire were to get away and not get suppressed, then that whole landscape could burn much more extensively, much more intensely than it would have burned in 1936. So the kind of paradox with suppression is the longer you do it, the harder it gets to keep doing it. Every time you suppress a fire, you've got fuel that would otherwise have been burned in that fire that's still hanging around, ready for the next fire to burn. And so a legacy of fire suppression leaves a lot of landscapes in this condition where if a fire gets into them, they are going to burn really extensively and really intensely and really dangerously to any people that are in the pathway of that fire. So to counteract that, we might try to remove some of that fuel. We might try to find ways to get rid of that fuel so that it doesn't become the basis for a really dangerous fire. And there are two main ways that we might reduce that fuel. One is through what we call prescribed fire. So these are deliberately lit fires. So we deliberately light the area on fire under controlled conditions. So we try to pick days when the weather is not blazing hot and bone dry, and when there's not a lot of wind, where we think we can keep the fire under control, but allow it to consume a lot of the fuel. And if we do that, then there's less fuel, so a fire coming through won't be as big and intense. So this does have the downside that you are lighting an actual fire, and so it's, number one, going to produce a bunch of smoke. And so that can be unpleasant or even potentially harmful to the health of people that are in the way of that smoke. Now, that's less of a risk than they would get if a big, really intense wildfire were to come through and burn that fuel, but it is still smoke being produced. There's always a risk of escape, and there have been some major wildfires that have started because somebody was doing a prescribed fire and they miscalculated something and it got out of hand and burned into areas they weren't planning for it to go into, and got out of control and became a major wildfire. So there are those risks to using prescribed fire. On the other hand, prescribed fire is more consistent with indigenous fire practices. And so there are a lot of places where there have been efforts to restore indigenous fire practices to the land, and conducting prescribed fires is one of the big things that they are doing. So even if it's not being a prescribed fire isn't being conducted by an indigenous community, it can resemble indigenous fire practices in some in some ways. And one of the other videos I'm going to have you watch, you're going to get to see some indigenous fire management. So prescribed fire is one thing we might do to reduce fuel. The other thing we might do is mechanical removal, where we go in and cut down and carry away these fuels. So that eliminates those risks from an escaped fire or producing smoke, but it has some downsides of its own. So one that I forgot to put on the slide here is it typically is much more expensive per acre treated than prescribed fire. It doesn't mimic ecological processes in the same way that prescribed fire does. So all of the effects that fire might have on the ecosystem that you could get from a prescribed fire, you're not going to get from mechanical removal, just going in and mowing and sawing things down. And there's also the catch that in order to finance mechanical removal, this is often done by companies that then take some of what they've removed and sell it as, wood for making whatever stuff we might want to make out of wood. So that can help cut those costs. However, the most economically desirable fuels to remove are not the same as the ones that are most likely to burn if a fire comes through. So in terms of reducing the fire risk, we're really interested in getting rid of a lot of the smaller fuels because they burn more easily, they can catch in a smaller fire. But what you're going to get the most money for extracting are the big trees. So there's this kind of trade-off that if you are trying to reduce fuel by logging, the trees that the loggers want are not necessarily the ones that the fire managers most want to get rid of. So then moving on to our third component of fire risk is climate change. So we've been talking a bunch in our recent lessons about climate change, so you probably or hopefully have a good general understanding of the phenomenon of climate change. And so we can connect that to wildfire. So on a very basic level, a warmer climate means you can have more frequent and more severe fires, all else being equal, right? Because weather is a key component of our fire triangle. So if the weather is warmer, then that is going to encourage fires. And in particular, what this manifests are, first, more extreme fire weather days. So if we are measuring the weather conditions and how conducive they are to fires spreading and getting out of hand, you get more days that hit the extreme levels on the fire danger index when you have a warmer climate. You also get a longer fire season. So the graph there is showing that for the Western United States is the length of the fire season, the length of the period during the year in which we have fires happening. So that fire season is becoming longer and longer over time. So you can see that there have been some fire seasons out west where we've had over 300 days in the fire season. So that's practically a fire year, right? There's very little time off if your last fire happens and then a month later the first fire, or 2 months later the first fire the next season starts off. You're not really having an off season in that case. So we're seeing lengthening fire seasons. So more opportunities for fire to burn throughout the year. And we also are seeing warmer nights. So when we look at the effects of a warming climate, what we see is that nights are getting warmer faster than the days are. So the increase in daytime temperatures is slower than the increase in nighttime temperatures. And in the case of fire, that makes a big difference because the cooling off during the night tends to reduce the intensity and the spread of fires. So the fires kind of quiet down overnight and then ramp up again during the day and then quiet down during the night. That's the usual pattern that you see with a fire. But if it doesn't get cool during the night, then the fire is going to continue to burn intensely through the night. It's not going to have to slow down and start back up on that day-night cycle. And so that's going to mean that fire is going to burn more areas, going to be harder to control. So a warmer climate has a pretty straightforward relationship with increasing danger from wildfires. The other element of climate, of course, is precipitation. And we've said that the effects of climate change on precipitation are kind of mixed, that we're expecting to see some areas get wetter, some areas get drier. In terms of fire, if an area gets drier, that could encourage more fire by drying out that fuel. So our fuel will burn more easily if it's dry. So drought can encourage more fires to happen. And some of the really big catastrophic fires that we've seen recently, like the big fires in Los Angeles last winter, were following really historic droughts. That fuel had gotten so dry that it burned so easily. So dry conditions can encourage fires, but increased precipitation actually can encourage fires too, because it enables the growth of more fuel. Because if you have no fuel, if nothing has grown there, you can't have a fire. There's nothing to burn. So rain encourages more growth of fuel, which can then fuel more fires. And so one thing that we're seeing happening in some areas that is sort of the most dangerous combination of these is referred to sometimes as a whiplash effect, where you get a rapid cycling between wet and dry. So you get wet conditions that encourage big growth of fuel, and then dry conditions that dry all that fuel out and get it ready to burn. So if you get that combination, that back-to-back wet and dry, that can actually be the most dangerous precipitation situation for making fires bigger and more dangerous. So looking forward into the future, our climate models predict overall increasing wildfire activity. So sort of the big picture general trend is for increasing wildfire under all of our different climate change scenarios that we've modeled. But the impacts are highly geographically uneven. So they're not playing out the same everywhere. So these two maps come from some research done by the US EPA, where they're looking at the expected change in the amount of fire that we'd see in the future. And they've got these two points in time, mid-century, so middle of the 21st century, and then the end of the 21st century. And what you can see is that different parts of the country are expected to have different effects from fire. So there are some areas like the Dakotas, Texas, the far west are expected to see really big increases in the amount of fire. So big increases in the area burned in those areas. But then we have other places that are expected to actually see decreases in the area burned. So New England, for example, or Florida, they're expecting to actually see less area burning. So this is that trade-off between changes in different types of precipitation and changes in temperature. So the whole country is getting warmer. Some areas are getting wetter fast enough that offsets the increase in temperature, that it's getting too wet to burn frequently. And here in Pennsylvania, we're kind of on the edge between those. So some parts of the state you can see, sort of roughly the northern and eastern parts of the state. This study is saying we're probably going to see a small decrease in acres burned, but then the southern and western parts of the state probably going to see some increases in areas burned. So effect here in Pennsylvania, not quite as dramatic as it's going to be likely in other parts of the country. In terms of fires burning right here in the state, we have to keep in mind that if any place west of us is seeing increased fires, that's going to mean increased smoke for us, because the winds usually blow from the west to the east. So all of those increased fires out west could still impact our air quality, even if we're not seeing increased fires happening right in our backyards. And so then finally, I want to talk about another example of an amplifying feedback. So we talked in an earlier lesson about the ice albedo feedback, where increasing temperatures melt sea ice, which decreases the albedo, which then contributes to increased temperatures. This is an amplifying feedback. Things are getting sort of snowballing in a worse direction. Or maybe snowball isn't the right metaphor for global warming, but you know what I mean. So we see another amplifying feedback here with wildfire. So if we have increased temperatures and those lead to increased wildfires emit CO2. Right? That is one of the byproducts of combustion is carbon dioxide. So our fires are releasing more CO2 into the atmosphere. And of course, if we add more CO2 to the atmosphere, that's going to increase the greenhouse effect and increase our temperatures. So you see this amplifying feedback. Higher temperatures mean more wildfire, which means more CO2 emissions, which means higher temperature. So it's making the cycle go more and more. Now, there is a long-run balancing effect if the burned ecosystems regrow. Because if you remember your carbon cycle, when carbon dioxide is released from the biosphere through either respiration from animals breathing out, or through combustion, which chemically same kind of process, it releases CO2, things burn, releases CO2 into the atmosphere. Then that CO2 comes back out of the atmosphere through photosynthesis. And so if you burn a forest, release a whole bunch of CO2 into the atmosphere, but then that forest regrows back the way it was, it's going to regrow by pulling CO2 back out of the atmosphere. So in the long run, the regrowth of that forest will balance things back out. Now, a couple caveats there. One is long run may be a very long run. It may take hundreds of years for that forest to regrow and to pull in as much carbon as had been released when it burned. So we've got a long period of having more CO2 in the atmosphere to deal with before it balances itself back out. And the other caveat is that we can't count on ecosystems regrowing in the same way that they were after they've burned. So there are a number of reasons that a ecosystem that burns in a wildfire may not regrow back the same way that it was. So you may have climate change itself may alter the growing conditions. And so, a forest that might have been able to grow in the past in that area no longer can grow there. And so it's not going to pull that CO2 back out. People may do stuff with that land. So you may see, farms or cattle pastures put in that area, and that will prevent the previous ecosystem from regrowing. You may have invasive species that move into that area. So there are a number of species in different parts of the world that have that are able to really quickly regrow in burned areas and then basically lock out the previous ecosystem from regrowing there and shift it into an ecosystem that is sequestering less carbon. So usually that will be certain types of grasses that will grow really quickly into burned areas and prevent big trees from growing. And so then those grasses are now creating a new ecosystem that is not sequestering as much carbon. And so that would be an example of something that would prevent the regrowth of that original forest and prevent that long run balancing out of this feedback loop. So I'm going to end it there, and hopefully you learned some interesting things, and I'll see you next time.